Okay, we're going to go over chapter 1.6, Photoelectron Spectroscopy. Now, photoelectron spectroscopy probably sounds similar to some of the things that we've talked about, like photons, which are small packets of light, and electrons. And so here it talks about how photoelectron spectroscopy was formerly known as X-ray electron spectroscopy, and it uses a monochromatic beam of X-rays at a solid sample. So this process is like what they describe it as kicking balls out of some ditches. And to help you, you have like a highly trained kicker who is consistently kicking a ball with the same amount of energy. Now, one ball emerges with 70 joules of kinetic energy, so we know that it required only 30 joules to escape from the ditch. So the escape energy was 30 joules. Now, two balls emerge with only 55 joules of kinetic energy. So we know it only took 45 to escape. So what we write down is that escape energy, or something called the ionization energy. Right? And ionization energy, as you guys know, is the energy required to remove an electron from its orbit. Okay, so what do we have here? So we have this process is virtually identical to the ones to determine the first ionization energy of an atom, except that we are only able to remove one electron from the valence shell. Using a very high UV or X-ray photon, we're able to remove core electrons as well and build up a complete picture of the electronic configuration. And so this is what we kind of see. We see these peaks, and these peaks tell us information about, one, how many electrons are present, and then two, what is the binding energy. So the more to the left, so you'll see here, this is a new tool, so you got to be patient with me. So here, this peak here has much more binding energy, say, than this peak here, because its binding energy, as you see here, is much greater. Okay, so here they're saying that, we already know s orbitals have 2 electrons, p orbitals have 6 electrons, d orbitals have 10, and so, the signal must be for 2s orbital confirms 2 electrons. So we know this one has 2 electrons. We know this one has 2 electrons. We know this one has 6. We know this one has 2 right here. It's kind of covered by this line. And then this one has 3. So what they're saying is that its complete electron configuration would be right here. 1s2, 2s2, 2p6, 3s2, 3p3. So if we look that up on the periodic table, or if we add up the electrons, that's 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. Something with 15 electrons would be phosphorus, and that's one way we could figure that out. Okay. And then this is Coulomb's law, and Coulomb's law is important. And so what that is saying is that so both hydrogen, which is 1s1 right here, 1s1, and helium, which is 1s2, they have a similar electron configuration, but you would notice that it takes a little bit more energy to remove from helium. So, it takes a little bit more energy to remove from helium. Whilst you might predict that the extra repulsions caused by having 2 electrons in the 1s orbital would cause the orbital to expand further out from the nucleus, increasing R and therefore decreasing F. The opposite is happening. F must be increasing as more energy is needed to remove the electrons. So you are looking at these values here. And what they're saying basically is this F value is proportional to Q1 times Q2 divided by R squared. Okay, so it says lithium and beryllium have both 1s and 2s orbitals. The 2s orbitals are further from the nucleus as are further from the nucleus, so the increased R means that the F has decreased, making it easier to remove 2s electrons than 1s electrons. Well, that would make sense since they're further away from the nucleus. But what the Coulomb law basically says, that it's a relationship between the force between two charged objects. The force between 2 points is proportional to the product of the charges, and so inversely proportional to the square of the distance between them. And that's what they're asking us to do. So here, this F, here, let me see, can I just, right here. So this F, this is electrostatic forces, and then Q1 and Q2 here, these are just the charges. And this is the distance in between. This is the distance. R is the distance in between. I'm surprised they didn't break down the terms here. Okay, so excuse my handwriting. This is my first time using this gadget, and so in Coulomb's law, you also have something called the constant. They don't write the constant here. So if you wanted to write it quite literally, you would write F equals K, and then the absolute value of Q1 times this part they had, right? Q2, the absolute value, remember that, over R squared. And this K value here, every time, is going to be 8.9 times 8.9 times 10 to the 9th. And I believe it is nanometers squared over C squared. Okay, so we can calculate that. We will have to calculate that in this lesson. So let's move on. Let's move forward. Okay, question number 1. It says here, the complete photoelectron spectrum of an element is given above. Which of the following electron configurations? Oh, so this is an easy one. So I would say like this is 1s2, this is 2s2 right here. This is 3p, no, not 3. How do I fix this? I guess I don't know how to fix it right now. I'll just write 2p, and if you look here, it's 1, 2, 3, 4, 5, 6, 2p6. Okay, and then 3s2, and then 3p1, 2, 3. So 3p3. So that would be B. Okay, now I don't know what's going to happen when I scroll down. Oh, nice. It keeps all of this intact. Okay. And then here it says the complete photoelectron spectrum for an element is shown above. Which of the following observations would provide evidence that the spectrum is consistent with the atomic model of the element? So off the bat, we would say this is one. Oh, sorry. That I did not need. Excuse me. This is all very new to me. Okay, so I want to write with the pen. Okay, hopefully it'll give me the ability to do that now. Okay, so here this would be 1s2, right? Because it's 1, 2, and then it would be 2s1 because there's only one here. So if you add up these electrons, you would find that there would be 3 electrons total, right? And so that would be lithium, right? And so if it's lithium, let's look at the answer choices here. So we have the complete photoelectron spectrum of an element is shown above. Which of the following observations would provide evidence that the spectrum is consistent with the atomic model of the element? So a neutral atom of the element contains exactly 2 electrons. We know there's 3 electrons here, so we know A can't be right. The element does not react with other elements to form compounds. That is not true. Li plus is charged, right? And so it would react with other things like OH minus. Those two things would react. So B is not correct. And so in its compounds, the element tends to form ions with a charge of +1. We just saw that here, Li plus 1. And we know that because it's 1 electron short of filling its. So Li's Bohr model, as you guys would know, would be, the first shell would have 2, and then the next shell, would have 1, and it would be itching to get rid of this 1, so it can have a octet, a full ring. So the answer would be C for this one. It definitely wouldn't end up with a charge of +3, right? Because there's enough protons and electrons to make its charge neutral. There's no way it would be +3. Okay, moving on to the next question. Okay. Here it says the photoelectron spectrum for the element nitrogen is represented above. So this is supposed to be nitrogen, and if I remember, nitrogen has an atomic number of 7. Atomic number of 7, right? So that means it should be 7 electrons. Which of the following best explains how the spectrum is consistent with the electron shell? Okay, so we have 1s2, 2s2, 2p3, and so 2 plus 2 plus 3 is 7. Okay, all right, so we know that the binding energy here is strong. This is a strong binding, strong. And we also know that the binding energy here is weak because it is, the numbers here are just simply smaller. Binding energy increases this way, okay? Okay, so let's look at the answer choices. The leftmost peak represents the valence electrons. No, that wouldn't be. 1s2 does not represent the valence electron, so this is wrong. The two peaks on the right have a total of 3 electrons. That's not true. 2s2 plus 2p3, there's right here, there's 5 electrons, right? So it's definitely not B. The electrons in the 1s sublevel have the smallest no, 1s has the strongest, right? So it would not be this. And just by process of elimination, you know it's D. But let's read the answer. It says the electrons in the 2p sublevel, right here, 2p, have the smallest. And as we saw here, you could just read this and see that the binding energy is smallest here. And so the answer is D. Okay, moving on. Okay, next question. A sample containing atoms of carbon and fluorine were analyzed using X-ray photoelectron spectroscopy. The portion of the spectrum showing 1s peaks for atoms of the two elements is shown opposite. So here's the 1s, this is for one of them, and this here is for the other one. Okay, so both of them are 1s. Okay, which of the following correctly identifies the 1s peak for the F atoms and provides, which of the following correctly identifies the 1s peak? Oh, so these are both 1s peak. They're asking which one would it be for the F molecule. So, well, first of all, we know this one is much higher. This one has a stronger binding energy. Okay, and so we would just figure out which one, so stronger binding energy means that there's a higher a nuclear charge. So it's a higher, nuclear charge. Okay, so if we look, let's see, a peak X would be, they're saying peak, this is peak X, would be has a smaller first ionization energy than C has, and that wouldn't really make sense because F has a larger ionization energy, and ionization energy, I think we went over this in the last one, is usually up in the corner. The one is the higher up and up to the corner, right? And so because fluorine has more protons and more electrons, then that means it would have a higher nuclear charge, because I believe carbon's atomic number is 6, and fluorine's atomic number is 9. So it would have a higher ionization energy and a stronger nuclear reaction, and thus a stronger binding energy. Just because that the 1s electrons are more tightly bound and they have a higher binding energy, because its electronegativity is higher, its nuclear charge is higher, it has more protons that matches the electrons, they hold them tighter. So, okay, so peak X, because fluorine has, yeah, that's exactly what we said. It has a greater nuclear charge than C has, so that would be B. Definitely not, because it has a smaller first ion. It's a greater first ionization energy. So these two concepts, they go hand in hand. It has a higher nuclear charge, and so it has a stronger binding energy. Next question. Okay. The photoelectron spectrum of the 1s electrons of two isoelectronic species, calcium 2 plus and Ar are shown opposite. Okay, so these are the two, right? Which of the following correctly identifies the species associated with peak X and provides a valid justification? Okay, so we have calcium 2 plus, and we have argon, right? And so that's argon just as it is regularly. And so if we look up Ca, its atomic number is 20, I believe, and Ar atomic number is 18. But in this case, it's lost 2 of its electrons. So right here, it has 18 electrons, and this has 18 electrons as well. So they have the same amount of electrons. This is called a phenomenon where it's called isoelectronic. Okay, isoelectronic. And that just means they have the same number of electrons. But I've always taught you that they might have this the same amount of electrons, but because they're two different things, there's one thing you can't change about them, and that's the number of protons, which is why I mentioned this. So if there is 20, and so this is automatically the number of protons here, right? And so automatically we know, right, that calcium has 20 protons and 18 electrons. So that means its binding would be stronger because there's 20 positive charges and it's just stronger pull here because there's just more magnets, let's say, at play. And so naturally, if you have 20 protons versus 18 protons, you end up pulling these electrons in tighter here. And so it'll give her a higher binding energy. So let's kind of look for that. So it says which would be associated with the peak X. So we already know peak X would have to be Ca. So we could remove these two. And Ca, because Ca2 plus, because its nuclear mass is greater. No, we didn't talk about mass. Mass has nothing to do with it. Weight has nothing to do with charge and pull. So we could take this out as well. And then lastly, Ca, because its nucleus has 2 more protons. Yeah, that's what we talked about. It has 2 more protons. And so then the nucleus of Ar has, and so they pull these electrons in closer. And so your answer is D. Okay, moving on. Okay. The photoelectron spectra opposite show the energy required to remove a 1s electron from a nitrogen atom and from an oxygen atom. So this is nitrogen and this is oxygen. And so one shows about 400, right? And the other one shows about, let's say, 550. Right? So they're saying that oxygen has a stronger binding energy. And so they're asking, which of the following statements best accounts for the peak in the upper spectrum being to the right of the peak in the lower spectrum? Now, let's say nitrogen atoms have a half-filled p subshell. And even if it did, that doesn't factor into removing the 1s electron. So I would take this out. They don't even show the peaks for the p subshell. Then it says there are more electron-electron repulsion in oxygen atoms. Then now, why would the repulsion be greater in oxygen atoms, right? Why would in outer shells there may be some repulsion, but that doesn't explain, why it's easier to remove an electron in the 1s. Remember, this question is asking about removing 1s in the innermost shell. The next one is electrons in the p subshell of oxygens provide more shielding than electrons in the p of nitrogen atoms. And I guess you could consider that, but extra shielding would decrease the binding energy, right? So if there was more shielding, it would decrease it. Since it says oxygen atoms provide more shielding, it would have decreased this for the p subshell, right? And so that can't be the cause, right? And so lastly, nitrogen atoms have a smaller nuclear charge. Remember, nuclear charge has directly to do with the binding energy. And because nitrogen has a smaller nuclear charge, it thus has a smaller binding energy right here, as we see. And so it is D. So this, it's kind of, these graphs are kind of straightforward. You could have deduced a lot of this. Now let's see the freestanding questions. I believe these are the AP classroom questions. Okay. So this question asks about the complete photoelectron spectrum of an atom in its ground state is represented below. Write the ground state electron configuration of the element. So that just means that it's probably lost a couple of its electrons. And so let's see. So in its ground state, we see the first one is 1s1. So I'm writing 1s1. And the next one here is 2s1. And then there's 3. So 2p3. Now we're writing it based on the chart. We're not writing it with its electron configuration and its orbitals full. And then we have 3s1. Then we have 3p3. And then we have 4s1. Now, if we add all this up, we would get, let's see, 1 plus 1 plus 3 is 5, plus 1 is 6, plus 3 is 9, plus 1 is 10 electrons. And if you look at the periodic table, 10 electrons would be neon. So that would be neon. Okay. And then it asks, calculate the wavelength in meters of the electromagnetic radiation needed to remove an electron from the valence shell of this atom. So if you look here, the valence shell would be right here. So that would be 0.980 times 10 to the negative 18. It's the valence electron. So, if that is the case, the number of electrons in the peak suggests that the element is in period 4, right? And if we look up what would be in 4s1, that would be K or potassium. Okay, and for this to make sense, if we fill all these in, we would get total of 19. So that's potassium's atomic number. So the atomic number of 19. Right, and so if you filled all of this up, then it would be basically AR. I'm not going to write out all of it. And then 4s1. And so that would it would be right here. 0. Let's just put an arrow. 0.980 times 10 to the negative 18. And so we would plug this in to the how to calculate the wavelength of another. So what we would do is we would calculate the wavelength is equal to h C divided by E. And so to calculate the wavelength, we would have our constant for H, which is 6.626 times 10 to the negative 34. Okay, and we multiply that by C, which is 3 times 10 to the 8th. Sorry, first time using this. 10 to the 8th. And we divide that by our energy, which is E. Okay, and then we got 0.980 times 10 to the negative 18. And we get, so if we do that, so that's 6.26 times 10 to the negative 34 times 3 times 10 to the 8th. And that's 1.9878 times 10 to the negative 25th divided by 0.980 times 10 to the negative 18th. And that kind of gives it away. 1.9 over, it's like approximately 2. So that's 2. Sorry about that. 2 times, let's say approximately. And so if we're dividing negative 25 by negative 18, you just subtract the 2 and you get 10 to the negative 7 meters. And that is how you calculate. Sorry. Again, I'm new to the platform. So that's a 2 times 10 to the negative 7 meters. And so that's how you would calculate the wavelength. Next question. Okay. Based on the photoelectronic spectrum, identify the unknown element and write its electron configuration. So again, this is pretty easy. We write 1s2, 2s2, 2p6, 3s2, 3p3. Now, if we just add up all the electrons, that's 2 plus 2 is 4, plus 6 is 10, plus 2 plus 3 is 15. So 15 electrons. There's only one thing that has 15 electrons, and that's phosphorus. So P, aka phosphorus. Again, this question, I think that's all it asks. To identify the unknown element, and we did that. And then lastly, it says consider the element in the periodic table next to the right of the element, next to phosphorus. So I believe next to phosphorus is sulfur. Okay, so there's phosphorus, and then there's next to it is sulfur. Okay, and would the peak of the element be to the right or the left? Would be it to the left of, or the right of, or the same position? Right, so it would never be the same position, right? And so the peak here, I think this is the peak that they're asking about. This is the only peak that would be different, and so. This S would have just as many electrons. It would just have one more electron, right? It would have one more electron. So this would have one more electron. And so this would also have one more proton, right? And because of that, it would have a greater ionization energy, which I taught you guys about. It was in last lesson too, 1.5 ionization energy. And therefore, it would have a greater nuclear charge. So it would have a greater, think about it, there's more magnets here at play, right? This one has 15, phosphorus has 15 protons. and 15 electrons. And this here has 16 protons and then 16 electrons. So it has one more electron and one more proton. So it has a greater ionization energy, and then it has a greater nuclear charge. Excuse my handwriting. And lastly, therefore, it would have a greater binding energy. And that's why it would appear to the left. It would be, its binding energy would be greater. And it would pull its electrons in tighter. All right, that's all.